Okay, yesterday we started to talk about this exercise about one possible application of piezo actuators. So mechanical actuators made up of a stack of PZT, so piezo materials, that are most of the time employed for, say, very fast, accurate movement in inkjet printers or in, say, photograph applications, medical electronics, and also in the, for example, piezo injectors in vehicle applications like this one. Here you have the circuits we have to design, which is the typical half bridge connected to the capacitor CP. CP for me is the equivalent model for the piezo material that is operated below the first resonance. And in that situation, I have the data that are indicated in the slides. So we have a burst of pulses that we have to apply to these piezo materials in order to have, let's say, a sequence of injection. Okay, here when the voltage applied to the piezo materials hit at the maximum value, Vp max, here the injector is fully open. So here in this part, here, etc., we have the spray of the fuel into the combustion chamber of the engine. While when the voltage Vp is 0, then here the injector is, let's say, closed. No injection of fuel into the combustion chamber is carried out in that situation. Okay, we have 10 of these pulses in a, say, burst cycle, which is called TB, 10 milliseconds. The period for each of these injection is, let's say, 1 millisecond, TI. I don't know exactly the width of this pulse because it depends on several parameters, like, for example, the temperature of the engine, the speed of rotation, etc. So we have to optimize the injection of the fuel upon several parameters monitored in real time. And all this cycle is about the cycle 20 milliseconds. Okay, so these are our data. The first thing that we have to consider is that, say, the TI pulse. Okay, so let me just consider this pulse here in the next page. So Vp let me put here TI, so TI 1 millisecond. Now zoom in this waveform. The waveform has not steep edges, okay, because remember that we cannot accelerate too much the elongation, the deformation of the piezo materials to avoid, say, mechanical damages. In particular, we have this data here that limits the maximum time rate of change of this voltage Vp. So we have something like this. Okay, so this quantity here, like this one, is exactly the Vp over the T, which is 2 volt microsecond. Remember that this value is 200 volt. So this means that I have a slope here that requires a T rise of 100 microsecond and at default, under the microsecond. Okay, this is just to say comply with the constraints of having this limitation here for 200 volt. What about the current? The current is something like this. We have a positive current during the rise up of the voltage. Then we have zero current here, and then we have negative current there. So this is Ti, this is T rise, so it is under the microsecond, this is T fall, under the microsecond. Remember that we have this relationship which holds for any capacitance, Cp dVp over dt. In our situation, Cp is by our specification 5 microfarad. The Vp over the T maximum value is 2 volt microsecond. So the maximum current that I have here, this value here is again 10 amp. Okay, so we have 10 amp here, negative 10 amp here. Okay. Two consideration. The first one is that this steep edge here is not possible. Okay, so we have to consider effectively to respect these constraints to have 1 amp per microsecond. So let's see what happens later on. The other consideration is that the area under these pulses here is a current versus time. This is a charge. Okay, this is a positive charge. This is a negative charge. The amount of the charge is the same because the area is the same. Okay, this charge is let's say 10 amp multiplied microsecond, so it is 1 millicoulomb. This charge here is positive because I'm saying providing charge to the capacitor in order to make possible for the voltage across the capacitor to rise up from 0 to 200 volt. Okay. In this pulse here, the charge is absorbed, is negative, so it enters into the output port of the half bridge because we are, say, removing charge from the capacitors in order for the voltage across it to, say, goes from 200 volt down to 0. Okay. How can you made it possible to have this variation of the average voltage at the output of the half bridge? Remember, this is done by changing the duty cycle, okay, the duty cycle of the half bridge. Okay, this is the discussion that we already had before. Let me call this Ti. So the duty cycle is something that increases from 0 to maximum level. Okay. Suppose that we are adopting the strategy to, say, use the transistor TA plus in the back operating mode, and then left open the TA plus for the rest of the interval. So we are just using, we call this A region. The phase B is this one. The phase C is this. Okay. So during the energization phase, we are providing energy, so we are in a back operating mode. And in that situation, we are using TA plus transistor. here, but we are not using TA minus. TA minus could be left open, for example. Okay. In the boost operating mode, in the phase B, the opposite is also true. We are using TA minus, and we are not using, so TA plus is left open. During the phase C, the holding phase, both transistors are left open. Okay, so basically the duty cycle is only employed during the phase A. Which is the maximum duty cycle that I have here. Duty cycle maximum is VP max over VD. And this quantity should be less than 1, okay? Because the duty cycle is a quantity that ranges from 0 to 1, okay? So the first thing that you have to do is to, say, choose the voltage VT that I can apply to the bridge. Since VP max is 200 volts, I can choose VD, for example, 250 volts. So the duty cycle maximum become 200 divided 250, which is 0.8. 0.8 here, from 0 to 0.8 in a T rise equal to 100 microseconds. So we can say that the duty cycle can be expressed as VP max for over VD, T divided T rise. Okay, this is for T, which is included in T rise. When you choose this value here for the voltage, pay attention that the value that you are choosing is something suitable to your switching devices. For example, what happens when this is your circuit, the half bridge, okay? The voltage VD, for example, we choose to be 250. The voltage VD is also the voltage that you have, for example, in each transistor when they are open. Okay, for example, when TA plus is closed and TA minus is open, the voltage across the transistor TA minus across the drain to the source is exactly the voltage VD, which is 250. Okay, so this voltage is a voltage that must not lead the transistor into the breakdown region. So you have to choose a transistor with a breakdown voltage which is higher than 250, of course. For example, 300 volt. Okay, if you choose not 250, but I don't know, 600 volts, okay, maybe it's difficult to find out a MOSFET having a very low Aron resistance with a breakdown voltage higher than 600 volts. So pay attention to choose a voltage that is compatible with the characteristic of, let's say, the commercially available transistor MOSFET that you have on the market. Okay, 250 is something which is, say, quite good. You can find MOSFET having breakdown voltage of, I don't know, 300 volt or even more with decent Aron resistance. What about the duty cycle dB? So this is the duty cycle. Sorry, not dB. Is now we have just a bridge to DA minus. I call it DA minus. DA minus is the duty cycle of the low side transistor TA minus, okay, which is typically 1 minus DA. The transistor TA minus is always off, except for the part B, so the energization phase here. Duty cycle in that situation goes from, say, 0.2, which is 1 minus 0.8, up to 1. Duty cycle of TA minus, okay? This means that dA is negative Vp max over Vd T minus Tfold over Tfold for all the time instants that are inside Tfold. So these are the two expressions of the duty cycle that you need for my specific strategies that I repeat myself are the strategies that see DA transistor TA plus only operated on and off during the rise and then always off, and TA minus only operated during the boost phase, the phase B, and on otherwise it is always open. For example, what does it mean? And this is something that we already saw in yesterday lecture. What does it mean having a duty cycle that rising from 0 to 0.8 hour in our application? It means that the unitary switching function, QA, of the transistor, QA, which is also the transistor, the QA of the top I-side transistor here, is something that starts with a very low value, say 0, and then increases up to up to 0.8. Okay, and what about QA minus, which is 1 minus QA, logical function, so this is the not version of QA, is something that goes from uh, 0.2 to 1 during the interval T4 under the microsecond. Now, let me just emphasize these the behavior I just drawn on the whiteboard. Okay, I have a duty cycle. Okay, I have a switching function Q, which is, let's say, increasing. Okay, in order to have a duty cycle which linearly increase from 0 to 0.8. Okay, so which is the period of this waveform? So which is the, say, the interval that we have between these pulses here, or also here, etc. Each period here is exactly the switch. So it is the switching time, the switching period of the transistor. Okay. How many of these pulses I have in T-rise or T4 in order to have this linear increasing of the duty cycle? I don't know. This is something that I have to decide now. Okay, so basically, I have to decide the switching period, switching frequency of the transistor. Which is a good choice. I have to say emulate this linear variation of the duty cycle. This one, for example, or also this one. How can I do that? If I have just two, say, periods, two pulses in T-rise, this can be done with an enough resolution, okay? Is enough to control exactly, say, in fine-tuning the duty cycle? Typically not. What happens is that I need several periods during, say, this T-rise or T4 interval in order to, let's say, modify the duty cycle slowly, and to have a variation that resemble, it's similar to that of a linear variation. So typically 10 to 20 switching period inside T-rise or T4. 10 to 20 TS within T-rise or T4. Let me choose for 20. Okay, so if I choose 20 TS during T-rise, I have that the switching period is T-rise over 20. So it is 100 microseconds over 20. It is 5 microseconds. So it means that the switching frequency is 1 over 5 microseconds. It is 200 kilohertz. So I'm going to switch transistor at 200 kilohertz. Okay, so on and off. If I choose this frequency, I know that there will be 20 pulses, okay, with increasing duty cycle. The width of each pulse is linearly increased slowly, in order to get, say, duty cycle ranging from 0 to 0.8 in a linear fashion. Okay? So let me put now another important point, which is the inductor design. L. We know that VL, which is the voltage across the inductor, is given by L, the IP over dt. We know that the data, the specifications we had at the beginning of this, say, exercise, provide us the maximum value for the IP over dt, which is 1 ampere over microsecond. So L is given by the VL over the IP over dt. This has a maximum value of 1 amp over microsecond. What about the voltage VL? VL is given by the voltage VAN, or function of T, minus the voltage across the capacitance. Okay. The voltage VL is the voltage here, and it is VAN minus VP. The worst case for the voltage across the inductor happens when the voltage VP is 0. And this happens at the beginning of each TI cycle, okay, when the cycle, the switching, the TI, when here we are here, the voltage VP is null, okay? Then this the charge that I'm providing by the half bridge makes possible for the voltage across the capacitor to rise up, okay, exactly in this way, okay, rise up here. But at the beginning of this cycle, the voltage is null, okay? So this is the worst case for the inductance. So that means that if I want to choose L should be VAN minus VP, the IP over the T maximum value. And if I put the worst case, I can see that L should be higher than VD over the IP, the T maximum. VD I choose for 250, 1 amp microsecond. And so L should be higher than 250 microhenry. Okay. For example, 270 microhenry if you find something normalized, or sometimes this is just something that you have to say design by your own, so you can choose your inductance say without any kind of normalization. But anyway, the inductance should be higher than this value, or maybe it's equal to this value. Let me focus a little bit on the issue, the problem that I highlighted here, okay, which is about the steep current edges that I have in this plot. Okay, if you see this plot here, you can see that the current should go from 0 to 10 amp instantaneously. Okay, but this is not possible. We have a limitation of 1 amp microsecond. Okay, so let me just include this discussion in the correct strategy for, say, providing the load current. So we saw that the duty cycle, supposing that we are talking about the rising edge, okay? So for any T that is included in T rise, we have that the duty cycle is provided by the expression that I gave you before, which is here. This one, okay? VP max over VD is 0.8, is this one. And so we have this 0.8 divided T rise, which is 100 microsecond. Zero 0.8 divided 100 microsecond multiplied T. So this is 8,000 T. We know that we have a switching period that is 5 microsecond. Okay, this is the switching frequency, TS. And so what about the current behavior? Let me put this in a graph just to simplify what I'm saying. Supposing that this is the first TI, sorry, the first TS, then I have 2 times TS, 3 times TS. So this is 5 micro, 10 microsecond, and say 15 microsecond. Each of these interval is a switching period. So we are looking inside this interval here. Okay, so for example, I just plotted 3 of these intervals, okay? So we are inside T rise, inside here. We are looking at this region, and we are, say, in the first 3 T-switch interval. Remember that we have 20 of these TS interval into T rise. Okay, so we are looking at a specific very beginning section of theorized interval, okay? Which is the voltage Vp. In the first interval, this is the expression of the duty cycle. So, for example, the duty cycle is in 5 microseconds as an interval. The duty cycle is, let me put this in a sort of table. So for the first TS, you have the duty cycle is 8,000 multiplied 5 microseconds, so the dA is 0.04. What does it mean in terms of on interval? So the interval in which the switching function u is I is Ts multiplied dA. Ts is 5 microseconds, 5 microseconds multiplied dA. This is 200 nanoseconds. So in this first interval here, I have a small, very thin pulse, which is 200 nanoseconds, okay, and this is Vd, and the rest is null. Okay, the duty cycle is exactly 0.04, okay, because we have to divide the interval, say, into 20 interval, the theorized interval into 20 sections, and the duty cycle has to range from 0 to 0.8. So the first one is 0.4. The second, this is the first one. The second TS interval has as a duty cycle 0.08, and T on is 400 nanoseconds. So as you can see, the duty cycle is, let's say, rising up. Now this is 400 nanoseconds. In the third TS interval, we have 0.12 as a duty cycle, and we have 600 nanoseconds. As a duty cycle, okay? If I plot all the 20 TS interval, okay, from say 0 to 100 microsecond, then the duty cycle at the end would be exactly 0.8. If you want here as the 20 TS, then we have exactly 0.8, which is exactly the duty cycle I need. Okay, so just focus the attention on the first 3 time intervals, okay, because this is the voltage Vp that I have due to the transistor Ta plus that is switching on and off. What about the current? The current is the current that flows through the inductor, okay? So when the transistor is off, here the current will be 0. Now, here the voltage applied at the output of the half bridge is 250. So we are in this situation. We have, say, the node A and the node B. Okay, we have a voltage which is 250 volts. We have the inductance. And then we have here the capacitance, Cp. And the capacitance has a voltage across it, which is Vp. What about Vp? We are at the beginning of our T-rise. Okay, so it is easy to suppose that the voltage across the capacitor is still 0 in this phase. Okay, so if you look at the current, we can see that the current is only due to the voltage across the inductance, which is basically 250. So we have a current here that rises up with a slope of 250 divided by L. basically, okay, because the voltage across the inductance is, across the capacitance is almost null. Then here, in this interval, the switch is open, so both the switch are left open. If both the switch are left open, what happens? Let me put this in this other page. We have a current here. Both the switch are left open. Remember that here I have a diode. The current is positive, so the current goes into this diode. Basically, the voltage across the diode is the voltage, the forward voltage of the diode. Okay. Supposing that typically VF is very small, can be neglected. Okay, suppose that we have an ideal diode, for example. So the voltage VL, which is VAN minus VP, VP is here, in that situation is more or less zero, because VAN, which is VF, is the small voltage across the on diode. And VP is not null, but is very low, because it's the small capacitance across this capacitor CP that is, say, charging up. So more or less it's very small. So we can see that the voltage across the inductor is very low, almost negligible in this very simple, say, computation giving you. So that means that the IP over the T, which is VL over L, is almost zero. So it means that the current is constant. So here the current has a behavior which is almost constant. It's not really constant. Basically, it has a negative slope, but it's very small. Okay, so we can consider it as a constant. Then we have another, say, pulses. Then you have again a slope, which is basically VD over L. So the same slope as before, neglecting again the voltage VP across the capacitor. Here the voltage basically is the same, constant, and then we have a same slope, VD over L. Okay. What is the current that I have at the end of the first TS? But it is the slope, which is 250 over L, multiply the time interval, which is 200 nanoseconds. So we can say that in the first time interval, we have that, let me put here, delta I peak in the any interval is the T on for that interval multiplied VT over L. So this means that, for example, for the first interval, we have T on, which is 200 nanosecond, 250 over 250 micro, and this is exactly 0.2 amp. So this is 0.2 amp. In the second interval, the current is 0. This is 0.4 plus 0.2 is 0.6 amp. This is 0.8 plus 0.4. This is 1.2 amp here. This value. So what happens that if you look at the complete behavior of the current with that process, with this process that I just say performed for the three steps that I showed you in the previous wide page, okay, you can see that supposing that this is the rise, the 100 microsecond here. What happens to the current? The current is null before this part, then it goes, say, we have, remember, interize, we have 20 of these intervals. Each of these interval is TS, switching, and the current goes exactly as I showed you before. This and this. So the behavior is something like this. So it is a ramp made by several steps, okay? I computed before. Of course, up to a certain point, I can neglect VP, then VP exists because the voltage across the capacitor start to rise up. So this voltage start to decrease, okay? And so we have something that is more similar to a triangular waveform, etc., etc. Something that is not well drawn. But the current goes in this way. Now, what is my ideal waveform for the current during device? The current during device is this one. Okay, 100 microseconds is theorized. The current from 0 goes instantaneously to 10 amp, remain constant, and then goes to 0. Okay, but I have this behavior during theorized. So put here the ideal behavior. The ideal behavior is something like this. And this is the real one. Okay, why I have a current in amp which is lower than the maximum value I reached here? Because remember what I said in the previous discussion, the area under the current is the charge, is the plus charge, which is 1 millicoulomb. That is exactly the charge I need for the voltage across the piezo actuator to increase from 0 to 200 volt. Okay, but in the same way, I can say that also the area under the real curve is a charge. And in order to rise up the voltage across the capacitor of 5 microfarad from 0 to 200 volt, I need the same charge. So the charge under this area is the same. But in order to have the same area, the yellow, say, box and the red curve, this peak value is much higher than 10 amp. So first situation, I increases too much the current that goes through the load. So, and this is something that, for example, if I have this as a specification, which is the maximum current that can flow, okay, this can as say something that violate this maximum current, okay, because this current here can be, let's say, twice the current or maybe higher. Then there is another drawback of this behavior, is concerning the voltage VP across the capacitor, because the voltage VP across the capacitor have the ideal behavior. Let me put this in yellow again here. So this rising up from 0 to 200 volt only if the current is constant, this one. If we have the red expression of the current, the behavior is what? But is VP is CP day IP over T. So I have to take into consideration the rate of change of the current, which is now is the red one, is totally different. And if you make some, say, computation, you can see that the behavior is something like this. So at the end, if you have the same charge plus Q under the red curve, of course, the voltage across the capacitor rise up from 0 to 200 volts. So that the 2 points at the ends, at the extreme of this interval are the same, but the behavior is totally different, okay? The behavior is a little bit more complicated, especially it's not linear. Remember what I said about the slope. The slope here should be 2 volt microsecond, because if you exceed this kind of slope, then you have physical damages into the piezo materials, okay? For example, because this is something that is constrained by the manufacturers. Manufacturers specify the maximum acceleration that you can have for your piezo. But if you look what happens in the real curve here, for example, okay, the slope here is higher than 2 volt microsecond. So this leads to permanent failures. Permanent damages. So letting the current increases naturally as it comes for, say our switching, say, behavior, as usually we are, say, used to, is not something that can be exploited. We have to change a little bit our strategy to make a transition which is more similar to the ideal one. Okay, what we can do in this for this case, we know that the IP over the T is 1 amp microsecond. Okay, so this is the maximum ramp of the current that I can have. Okay, so what does it mean? That I have, for example, in 10 microsecond, the current rises up to 10 amp with that specific slope. Okay, but 10 amp is exactly the current I'd like to have as a maximum current flowing to the load. Okay, this current here is 10 amp. So in which way I can exploit this fact? I can exploit the maximum slope for the current, but I know that the switching period is 5 microseconds, okay? Because I choose 200 kilohertz for the transistor switching frequency. So this means that 10 microseconds are 2 switching periods, okay? 5 plus 5. So if I close the TA plus, if I hold closed TA plus for 2 switching periods, instead of having it switched on and off, I simply close this transistor for 10 microseconds. The current through the load can ramp up to 10 amp with this specific rate of change. So my switch action is to take this transistor TA plus on for the first 2 TS. This is 250, and so also this voltage is 250. L is 250, for example, 250 microhenry, okay? And so if I choose this inductance, and this voltage at the beginning is, let's say, almost 0, voltage VP at the beginning is almost 0, okay, because it's not yet charged, then the current that flow here has exactly, let's say, a ramp, which is 1 amp microsecond. Okay, so if I take this transistor closed for the first two switching periods, okay, I force it to be closed, then the current can goes up exactly to 10 amp. So my, say, switching function QA is modified from the standard pulse width modulator in this way. This is T-rise that are 100 microsecond. I have 20 T-switch periods here that are 5 microsecond, 5, 5, 5, 5, etc. The unit resolution function is 1 for the first two periods. Okay, it's 1, making TA plus on for the first two periods, and then the duty cycle follows the standard, say, increasing, etc., law that make possible to have, say, the duty cycle at the end, which is 0.8. And here we have the first two periods that are on. So I starting from the third period. And the third period is, if I remember my table, where is here? So these are the first two periods in which I close the switch. So I can start from 0.12 up to 0.8. Okay, so what happens to the current? The current goes exactly, let's say, IP over T. T-rise. After 10 microseconds, the current has reached 10 amp. The slope is exactly 1 amp microsecond, so it is the maximum admissible. And then it happens that for other periods, I have something like this. Okay, so as you can see, the current, of course, we have some, say, ripple in the phase in which the current should be constant. Okay, but then what happens is that I have a characteristic which is much more similar to the ideal situation, to the case I'd like to have. Okay, what happens here in this part? In this part, I am, say, reducing the current. In order to reduce the current, I have both switches that are off. They are left open. Here we have a diode, which is the freewheeling diode for the current. The current is positive here, so flow through the diode. And so the voltage drop across this diode is, let's say, the capacitor here now has a voltage VP, which is the maximum voltage, because now the voltage across the capacitor is, say, 200 volt. Now it's fully charged. So we can say that VL is basically negative VP max. And so the IP over dt is negative VP max over L. If I choose L to be 250 microhenry, then the IP over the T is negative 200 volt over 250 microhenry, and this is negative 0.8 amp microsecond. So this slope here is not so fast as this one. Okay, the slope here is 0.8, more or less, amp over microsecond, because it depends on the voltage drop across the capacitor, which is now fully charged. Okay, so here we have a behavior which is not right, because we have this ripple, but basically we have a behavior which is, say, much more similar to the ideal case. The ideal case was something like this. I want to stress here. Okay. Questions about this discussion? As you can see, I'm trying to modify a little bit the strategy in order to withstand with my requirements, okay, to avoid, say, surprise. So let's consider something to get into a little bit more detail, just to see if it is clear what I'm discussing here. Okay, because let me see what happens about, for example, the voltage across the capacitor. Okay, what is the expression and the value that I can have, the behavior of the voltage Vp across the capacitor. Let me consider this charge. The charge which you have in this phase. Let me call this delta Q, okay, which is this charge. The charge that is needed that we have, let's say, after 10 microseconds. Okay, so the Q is an area. So 1/2 of the peak value is 10 amp, and the base is 10 microseconds. And this is 150 microcoulomb. Okay, this is the area of this triangle. Okay, and this is the charge that you are providing to your load after the first 10 microseconds. I want to compute which is the voltage across the capacitor Cp after 10 microseconds. Okay, so the voltage delta Vp across the capacitor is delta Q over Cp, which is 50 microcoulomb after 5 microfarads, and this is 10 volts. So this charge is able to increase the voltage across the capacitor from 0 to 10 volts. Okay. So what does it mean? That at the end of this interval, the voltage across the capacitor is 10 volts. It's no more 0. Remember my computation that I consider here. I say somewhat simplified analysis, saying that, okay, put me in a situation which I have for the first 10 microseconds, more or less 0 voltage across the capacitor. But now I can see that this is not really true, completely true, because at the end I have already 10 volts across this capacitor. So that means that this quantity here, this slope, is not always 1 amp. So it's decreasing a little bit. Okay. So it's not true that this slope is exactly linear in this way, because it is linear and constant to 1 amp microsecond only if the voltage Vp is null for the entire duration of 10 microseconds. This is not true because the voltage increases from 0 to 10 volt when you reach this value here. When you have 10 volt at the end, it means that with Vp, which is 10 volt, like we computed now, it means that the Ip over the T is no more Vd over L, but it's Vd minus 10 volt over L, which is 250 minus 10 over 250 microhenry. And this is 0.96 amp over microsecond. So it is not 1 amp over microsecond, but it's a little less. So it means that the current, if you look and you can simulate this, maybe you can see something like this. Just to be, say, a little bit more precise, the current has a behavior which is like this. The slope is almost 1 volt at the very beginning of this curve, then the slope increases a little bit, and at the end, here is 0.96 amp microsecond, while at the beginning here is 1 amp microsecond, more or less, okay? Just to be a little bit precise. This means that my voltage Vp, which follow this behavior, is something that has a parabolic behavior like this, say up to this. When it's constant, it's a parabolic value, and there's other behavior which is something like this. But anyway, this again is much better than what we get in a previous situation, okay? This curve here, remember that we have the expression of Ip, which is Cp, the Vp over the T. Okay, so when the current is almost linear, we have a parabolic version. When you have something which is not different, a different behavior. But anyway, this is just to be very precise. Nothing change our strategy. Okay, we can use this computation just to say fix main idea. Okay, when you simulate this, maybe you can see not a linear straight because the voltage is increasing across the capacitor, etc., etc. Let me put now a little bit stress on this behavior during this phase in which the current, ideal current, must be constant to 10 amp. Instead, we have a ripple, okay, because we have this behavior, the behavior of transistor that are switching on and off, okay? So when transistor is on, the current rises up. When the transistor is off, the current goes down a little bit. In that situation, we have the ripple, okay? We have an half bridge. Maybe you should remember, which is the maximum ripple that you can get for a left bridge. You should remember that the maximum ripple that I can have is for an F bridge, the supply divided for L F switch. And this happens when the duty cycle is 1F. We computed this value in one of the previous computation we had for the half bridge. Okay, and this is valid here because we are using the half bridge. This is 250 volt, and we have 250 microhenry, and then we have the switching frequency, which is 200 kilohertz. 1.25 amp. When the duty cycle is 1F. Duty cycle is 1F is a duty cycle that is employed here, but if you look what I say here, the duty cycle ranges from 0.12 to 0.8. So in between, okay, here there will be a point in which the duty cycle is, let's say, around 0.5. So it means that my ripple peak to peak here, when the duty cycle reaches this value, is a value which is more or less 1.25 amp. Okay, so my current is not 10 amp. If you want to consider the peak value of the current, the peak value of the current would be basically is 10 amp. Then you have the maximum is 1.25 amp. So max current is 10 plus 125 over 2. Okay, big value here. So we have 10.625 amp. The maximum current that you're for. This value is important for, say, the inductance, because inductor L should be chosen not only, say, according to the value, but also according to the maximum current that flows through it. Okay, you have to choose an inductor that has, say, larger than 250. Okay, in this computation I use exactly 250 microhenry, but with a current which is larger than 10.625 amp. Okay, because we have to ensure that the inductance goes now into the saturation of the core region for the nominal operation. Okay, the inductance is not to be saturated, otherwise the inductance goes to lower values, and this is not, say, good. Okay, problems, questions, whatever. Up to now, I focused the description about the, let's say, the energization phase, the, say, charging phase of the load. Let's have a look to the, let's say, discharging phase. The phase that I called B, my previous. Discharging phase, sometimes called the pooling phase. The energization phase, whatever. There are several different names for the same behavior, and the behavior is the following one. The voltage Vp from Vp max must be decreased. Okay, I have to get a, say, negative displacement of the piezo actuators from the maximum elongation down to the rest position in order to close the injectors. Okay, this is default, which is 100 microsecond. Okay, remember that the duty cycle here has a behavior which is, say, minus Vp max over Vd T minus default over default. So it's a duty cycle that decreases from 0.8 down to 0, the duty cycle of the I-side switch. Okay? And in this region, we are operating the half-bridge converter in its boost operating region. So we are absorbing power from the load, okay, and this power goes transitate through the half-bridge toward the VD supply. Okay, so let's have a look a little bit to this specific region that I called previously B. What are the devices that are, say, employed in this phase? Remember that TA plus is, say, left open, so we have just TA plus, and then I have the transistor TA minus. So this is the standard boost. Okay, the current is negative in this phase, so the current goes in this direction. The power flow is a power flow that translates from the right, okay, to the left. Boost operating mode. This transistor is TA minus, is say, is operated by a unitary switching function which is QA naught, okay, which is 1 minus QA, so the unitary switching function of the transistor TA plus. Since this is a boost, okay, we can consider that the input voltage of this boost is this one. This is the input voltage for my boost. Okay, the power translates from the right to the left. So in terms of, say, power flowing, the input source is the load, while the load now is the input PD. So this is the input side for boost. So let me call this V in boost. V in boost is VP. This VD here is the output side. V out of our boost. We found out that, say, the relationship between the input and the output for a boost converter. V out boost is the input boost multiplied 1 over 1 minus dA of the transistor we are using, dA minus, okay? Remember also that 1 minus dA minus is also dA plus, okay? Is the duty cycle of the top side transistor. We can also write this expression in this way, dA plus. Let me plot this function as a function of dA minus, or if you want, as a function of dA plus, since it exists this relationship here. We can have, say, both the horizontal axis. V out boost, I want to plot V out boost over V in boost. Okay, so the ratio between this quantity and this one versus the duty cycle. So when the duty cycle dA minus is null, duty cycle ranges from 0 to 1. When it is null, we have that this transfer function is 1. When the duty cycle dA minus is 1, this goes to infinite. This is possible. It's possible that when dA minus is 1, this asymptote is, goes to infinite. So it's possible to have an infinite voltage. What does it mean, dA minus equal to 1? dA minus equal to 1 means that this transistor is always closed. And when the transistor is always closed, then the voltage VAN, okay, is, let's say, 0. And so how can you have an output voltage, so it is the voltage VD, which is infinite? It's not possible. There is not energy transfer in that situation. It's something that is not, say, according to these equations, is not correct. The problem is that we are neglecting some parasitics. Okay, students of power electronics, I liked that they remember the same discussion we had in the course. We have this resistance here that are parasitics, something that you don't want in your circuit, but you have due to the real elements you are using. Okay, and the real elements are sometimes, most of the time, always, we have to say, parasitics in series or in parallel. For example, you have a resistance in series with the inductance due to the terminals, leads, etc. And you have also a very large resistance RP in parallel to the capacitor, which is the piezoelectric materials. Due to this quantity, this transfer function is a little bit modified. Okay, especially this curve is obtained for RL, which is 0, which is a DL case. But when you are increasing this resistance, okay, the curve is a little bit different. The behavior is something like this. If you increase RL over RP, you are having this behavior. Basically, all this curve at duty cycle, dA minus 1 goes to 0. And this is correct because when duty cycle dA minus 0, you have no energy transfer because the transistor is always closed. Okay, so decreasing RL increases the maximum point you can have here. Okay, so this is what happens. Okay, this behavior here, which is, let's say, a real boost, say, action, real boost operation, leads to specific behavior of the piezo actuator during this phase. Okay, if you look at this situation, I have to discharging the piezo actuators. So for all the duration of this phase, the energy, the power transitates from the piezo materials to the source. Okay, so basically I'm in a situation which I can recover energy. Okay, remember in motors this is the braking situation. Okay, we are recovering energy. We are not more providing energy to the load, but say we are absorbing this energy. But due to this behavior, this is not possible for the entire duration of my discharging phase. Okay, this is the point from which we can start say detailed explanation of this recovering energy phase, discharging phase. Okay, we can stop here, but next Tuesday we can start from this point to go further to discover what happens in this phase due to the specific behavior of any kind of real boost. Okay, have you any questions about the topic I explained now? Problems, issues, whatever? Okay, feel free to comment, to say, ask me whatever you have in mind. Okay, guys, if you have no questions, I wish you a nice day and weekend. We can see each other next Tuesday. Remember that in the afternoon of the next Tuesday, there will be the lab, okay, for the people who booked the seat to the airport. See you guys. Bye. Thank you.